Welcome to the new semester of Advanced Calculus. So here we're going to use the tools that we learned in Advanced Calculus 1 to study functions. And in particular, as a first step, we will introduce a notion of a continuous function, a notion of a limit of the function. Then we'll use that to study derivatives. And finally, we're going to look at rigorous underpinnings of integration. So first, let's recall what is a function. So to define a function, as you might remember, right, we need to specify a set, the domain. Then we need to specify the codomain in which the function is going to have values. So let's call this C. And then the function is a rule which will assign to each point in D some point in codomain C. So if X belongs to D, then this would be f of X. F is a rule. So F is a function. If for each point in D, there is a unique corresponding point in C. So again, this guy is a domain. The final set is a codomain. And then we also have a notion of range. Range of f is going to consist of all points y in C such that there exists an x in D such that f of x is equal to y. Right? So range of f then is going to be a subset of C. It doesn't have to be the entire set C itself, right? So for example, if I have a function f of x, y equal to f of x squared, y equal to x squared, then the domain is a set of all real numbers. Codomain is again the set of all real numbers, and the range is the set of positive real numbers, right? So let's define what R plus is. So R plus, I'm going to use it in the future as well, is a set of all x that are greater or equal than 0. All right. So we're only going to be interested in functions from a set of real numbers to a set of real numbers. So in this course, we always going to have f that starts in R and ends in R. So both domain and codomain would be a set of real numbers. In general, of course, this is not necessarily true, right? So for example, you can have functions from R2 to R, in which case this is just a standard function of two variables, or you can have a function from R to R2, and that would be a function which assigns a vector to every point on a real line, or a function from R2 to R2. If you recall, then this is something that is called a vector field, because to each point on the plane, this will assign a two-dimensional vector and so on. But in this case, we're going to keep the thing simple. So f is always going to act from a set of real numbers to a set of real numbers. Okay, so now that I recall the definition of a function, I want to look at what it means for the function to be continuous. And we're going to have the following definition. So definition number one, f is continuous at x0 that belongs to the domain D of your function if, so I'm going to write the definition first and then we'll discuss this. It is continuous at x0 if for any sequence xn such that the limit as n goes to infinity of xn is equal to x0, we have that the limit as n goes to infinity of f of xn is equal to f of x0. We're going to say also that f is continuous on the entire set D if f is continuous at all x0 in D. Okay, now let's make sense of this definition. Now you see that already I used our notion of a sequence that we introduced in Advanced Calculus 1. So just a quick sketch. So let's say we have a point x0 somewhere, and I have a function that is represented by a continuous curve. Now, what does it mean that we have a continuous curve? It means that simply I can draw the graph of f of x at the point x0 without, as we said back in just a regular Calc 1, if I can draw this graph without lifting the pen off the paper. Right, so this function is continuous at x0. In fact, clearly it is continuous everywhere where this function is defined, if it's defined by this graph. That because at all points, I'm drawing this curve without lifting the pen off the paper. And now our example. let's say I have a similar graph, but now at x0, we have a hole. So maybe this is x0, and this number will be y0. Clearly, I lifted the pen off the paper at x0, so this continues. And the third example, let me press this a little bit. And the third example will be a function that jumps at x0. Something like this, and then maybe like that. So x0, y0, and this is now f of x0. Again, this function should be discontinuous. At x0, it's obvious, right? By inspecting the graph. All right, so now let's compare this to our definition. In the first case, actually, let's make this f of x0. In the first case, let's say I pick any sequence of x's that converges to x0. So, right, so this would be an arbitrary sequence of xn. In fact, let me actually zoom in on this graph. So let's choose any sequence of x's that goes to x0, right? So the red is going to be that sequence of x's. Then corresponding to each x, there is a y. And clearly, right, if I look at, get rid of f of x0, if this is my x1, x2, etc., I have f of x1 up here, then f of x2, and of course, at the end of the day, I have f of x0. So as long as I have a sequence of x's that converges to x0, if I look at the sequence of a corresponding f of x, then clearly that sequence must converge to value of the function of at x, x0, so to f of x0. And so then the definition of continuity is satisfied. So clearly, as x goes to x0, f of x goes to f of x0, so therefore f is continuous at x0. Now, notice also that if I have another sequence which converges to x0 from the left, then the corresponding y's will do the same thing, right? So maybe x tilde 1, x tilde 2, etc. Then f of x tilde 1, f of x tilde 2, and so on. So as x values go to x0 from above, then you can see that f of xn values are going to converge to f of x0 from above as well. And so that means that any sequence of xn which converges to x0 from above will generate a sequence of f of xn which converges to f of x0 from above. Also, if I have a sequence which jumps from right to left or from left to right as x goes to x0, then again, the same thing is going to be true about f of x. F of x will go to f of x0, so the function is continuous. Let's look at our second example. What's the difference in this case? Once again, let me just use example of one sequence. Let's take sequence of xn that goes to x0. Then there is corresponding sequence of f of xn. x1, x2, etc. So then in this case, let's pose it the limit n goes to infinity of xn is equal to x0 is clearly the case for the sequence of red points that I drew there. Then as clearly, the limit as n goes to infinity of f of xn, so limit of these red points, is going to be y0. However, what about the value of f at x0? And you see that I have a hole here, right? So f of x0 is not defined, and so therefore limit n goes to infinity f of xn equal to f of x0, this statement is false. Right, and so if I can find one sequence for which limit of f of xn is not equal to f of x0, then the function is not continuous, because in my definition I said for all sequences it should be true. So then we're going to say in this case, so what do we observe? We observe that the limit of f of xn exists and is equal to the value of y0, which is the value, if the function had that value at x0, the function will become continuous. So we'll say in this case that f has a removable discontinuity at a point x0. Why is it removable? Because it's easy to remove this discontinuity simply by filling in the value of f at a point y0. All right, and let's look at the third case. So here, if I take a sequence of xn that converges to x0 from the left, and maybe I take a sequence of xn that converges to 0 from the right, then we will see that the limit of f of xn is going to be different, right? So for the purple sequence, let's call purple sequence again xn tilde, and the red sequence just xn. Then if I take the limit n goes to infinity of xn, I'm going to get x0, right? Because just clear from the picture. And if I take a limit n goes to infinity of f of xn, well, so in this case, xn converges to xn tilde converges to f of xn from above, converges to xn from above. Let's look at xn tilde first. And clearly, if I follow these points, they approach the point f of x0. So if xn tilde goes to x0 from above, then the limit of f of xn tilde is going to be f of x0, which is kind of nice, right? Because that's the definition of a continuity, right? If a sequence along x-axis goes to x0, then the corresponding sequence along y-axis goes to y0. But this has to be true for all possible sequences. So now if I take limit of xn, which is also x0, right? Limit of red points. However, for those, we see that f of xn will converge to y0. So limit n goes to infinity f of xn is y0. And then the function is discontinuous again, because I found a sequence along which limit of a function is not f of x0, it is something else. So this is called jump discontinuity. Clearly, this discontinuity is not removable anymore because just I cannot fill in the point, the lower point at x0, right? Because then what I'm going to get is not a function. I cannot fill that point also because then I'll have to release the point which is currently labeled f of x0. I'll have a hole there. So just jump discontinuity is not removable, right? Because there is no value of f of x0 which will make the graph continuous. Also, one other thing, if in this case I'm not going to plot it because the picture will be too busy. If I have, for example, a sequence of x's which converges to x0 and it jumps from right to left of x0, so maybe I take a red point and I take a blue point, and next red point, next blue point, next purple point, and so on. So I keep jumping from right to left. And I then will have a sequence xn which is still going to x0, but f of xn will not have a limit because f of xn is going to be alternatively either here somewhere or here somewhere. So it's going to be jumping between f of x0 and y0, and then the limit of that sequence does not exist at all. So just one more thing that I'm going to put here. So you have a jump discontinuity because y0 is not equal to f of x0. All right. But you also might remember that in Calculus 1, you also So the definition of the limit, which involved two parameters, epsilon and delta. And I'm going to turn to that now by considering the following theorem. And that's going to be the equivalent definition of continuity. And it is going to go as follows. F is continuous at x0 if and only if for every epsilon greater than 0 there exists a delta greater than 0 such that x minus x0 being less than delta will imply that f of x minus f of x0 is less than epsilon. Now, again, this should be a fairly intuitive definition. Let me again illustrate it by a picture. So we have a set of coordinate axes. We have some function f. I have a point x0. And what I'm saying in my theorem is the following, that let's pick an arbitrary epsilon greater than 0. So here is my f of x0. I'm going to pick an arbitrary epsilon greater than 0, and I'm going to consider the interval on which f of x minus f of x0 is less than epsilon. Now, what does it mean that f of x minus f of x0 is less than epsilon? It means that the distance between the value of y and f of x0 must be less than epsilon. So that means that I'm allowed to go up by the amount epsilon and down by the same amount epsilon. So the top point is going to be f of x0 plus epsilon, and the bottom point is f of x0 minus epsilon, right? Because that is a range in which y is allowed to vary if I impose this condition, f of x minus f of x0, magnitude is less than epsilon. All right, how do I ensure that, how do I choose x to ensure that f of x is going to fall within this interval? Well, I just follow my function backwards, right? And that means that if x is inside this interval, as long as x is inside this interval, then f of x is inside the prescribed interval of the size epsilon around f of x0. Well, but then if I examine this picture, then I see that it appears that the interval on the left is probably slightly longer than the interval on the right. And then if I choose a smaller of these two distances from x0 to the point on the left, x0 to the point on the right, I can just use that smaller distance as my range in x. Oops. So now the interval is symmetric. This will be x0 plus delta. This is x0 minus delta, and that is my definition. Delta in this case is going to be, again, the smaller of these two lengths. I have one length here, one length there. I want to make the interval symmetric, so I choose the smaller of these two lengths. And as a result, I get a symmetric interval around x0, such that if I apply f to every point inside that interval, the outcome is going to lie between f of x0 minus epsilon and f of x0 plus epsilon. And clearly, in this case, I should be able to do this construction for any point, for any value of epsilon, right? This construction can be done at x0 for any value of epsilon. And so that means that the function is continuous. And indeed, in this case, the function is continuous. Let's illustrate another example like that, except that in that case, I'm going to have a discontinuous function. So let's do the function with a jump. So once again, I have a set of coordinate axes. Except that now, let's make the function discontinuous. So we have a point x0, and I have a function that jumps like so. So f of x, x, y. Well, would the same construction work here? Okay, let's pick the number epsilon. Let's take f of x0. And I'm going to allow myself to go by distance epsilon from the point f of x0 along y-axis, right? So this would be f of x0 minus epsilon, of x0 plus epsilon, and f of x0 itself. So I chose epsilon like this. I'm now forcing f of x to be inside this interval. Well, so follow the same procedure as before. Maybe let's modify this function a little bit, like that. So go down onto x-axis. Go down to, oops, but this does not intersect the graph of the function. Right, so that means that I'm going to force my function to lie in the interval, inside the interval of a length 2 epsilon. So inside this interval, there are not going to be any points on the left side of x where values of x will lie inside this interval, right? Because this horizontal line is not going to intersect that bottom branch of the function. And so that means that x has to be inside this interval in order for us to satisfy the condition that f of x is less than the difference between f of x and f of x0 is less than epsilon. Okay, so but then I go to the left, to the right by some amount to stay inside this interval. I'm allowed to go by this much to the right along x-axis, but I'm not allowed to go to the left at all because there the values of the function will fall outside of this window. So then what is the value of delta that I can use? Just like in the previous example, delta is going to be a smaller of two numbers. How much I can go to the right and how much I can go to the left. Well, but in this case, delta is equal to 0, right? So therefore, here, delta is equal to 0. And if delta is equal to 0, then I'm not satisfying my condition that x minus x 0 must be less than delta, where delta is strictly greater than 0, right? So the function is discontinuous at x0. Okay, so with these two examples, we're going to end this lecture, and then I'll start next lecture by proving the theorem that I have just formulated.